Today my topic is homomorphism of rings. So what is the definition of homomorphism of rings? Let r comma plus comma dot and r dash comma plus comma dot to rings. A mapping f r to r dash is such that f of a plus b equal to f of a plus f of b, f of a b equal to f of a into f of b for all a comma b belongs to r. Then we say that f is homomorphism from r into r dash. So to define homomorphism of rings, we take two rings r comma r dash, and f is a mapping from r to r dash, and it satisfies two conditions. So the two conditions are f of a plus b equal to f of a plus f of b, f of a b equal to f of a into f of b for all a comma b belongs to r. Then we say that f is homomorphism from r into r dash. So homomorphism is nothing but it is a function from r to r dash. It satisfies two conditions. Then f is said to be homomorphism from r into r dash. So what are the two conditions? F of a plus b equal to f of a plus f of b, f of a b equal to f of a into f of b. Okay. Types of homomorphism. One is monomorphism, two is epimorphism, 3 is isomorphism, 4 is endomorphism, and last one, fifth one is automorphism. So these are the types of the homomorphism. The first one is monomorphism. To understand monomorphism, we know the f is one function. When we say that f is one function, f is one function from a to b if f of a equal f of b implies a equal to b, then we say that f is one function from a to b. So here we need definition of one function, because monomorphism is nothing but it is homomorphism plus 1 monomorphism is nothing but it is homomorphism plus 1. So the definition of monomorphism is, let r comma r dash be two rings and f r to r dash is said to be monomorphism if it is homomorphism and 1. If homomorphism plus 1, that is called monomorphism. Then we go for epimorphism. To understanding epimorphism, we need onto function. So when we say that f from a to b is onto function, for all b belongs to b, there exists a belongs to a such that f of a equal to b, then f is said to be onto homomorphism. We know that. So because the epimorphism is linked with onto homomorphism. So epimorphism is nothing but homomorphism plus onto. Epimorphism nothing but homomorphism plus onto. Therefore, and the epimorphism also called as onto homomorphism, because it is homomorphism plus onto. So that's why it is called onto homomorphism or epimorphism. So therefore the definition of epimorphism is, let r comma r dash be two rings. A mapping f r to r dash is said to be epimorphism if f is homomorphism and onto. Epimorphism also called as onto homomorphism. So epimorphism nothing but homomorphism plus onto. Then third one is isomorphism. So what is isomorphism? Isomorphism is nothing but homomorphism plus 1 plus onto, or homomorphism plus bijection. So isomorphism is nothing but homomorphism plus 1 and onto. So what is the definition of isomorphism? Let r comma r dash be two rings. A mapping f r to r dash is said to be isomorphism if f is homomorphism 1 and onto, then it is called isomorphism. So isomorphism is nothing but homomorphism plus 1 and onto. Next one is endomorphism and automorphism. So in function, generally f is a function from a to b, but in the case of identity function, we take from a to b. So self and generally function from a to b, but in some cases we can take function from a to a. Here also the homomorphism can be defined from r to r dash, or the homomorphism can be defined from r to r. If the homomorphism is defined from r to r, then it is called endomorphism. If the homomorphism defined from R to R, it is called endomorphism. If isomorphism is defined from R to R, it is called automorphism. Therefore, what is the definition of endomorphism? That R bearing a mapping F R to R is said to be endomorphism if F is homomorphism. So endomorphism is nothing but self homomorphism. Endomorphism is nothing but self homomorphism. And the last one is automorphism. Automorphism nothing but self isomorphism. And in the case of R to R dash, we take R to R. So if you take R to R, and if it is isomorphism, then it is called automorphism. So what is the definition of automorphism? That R bearing a mapping F R to R dash is said to be automorphism if F is homomorphism 1 1 and on 2. Then F is said to be isomorphism on R. Then F is said to be isomorphism on R, nothing but automorphism. So these are the types of the homomorphism. Just I will revise all these things. So in this chapter we learned homomorphism, definition of homomorphism, types of homomorphism. So homomorphism is nothing but it is a function from R to R dash, it satisfies the two conditions, then F is said to be homomorphism. Monomorphism is nothing but homomorphism plus 1 1. Epimorphism nothing but homomorphism plus onto. Isomorphism is nothing but homomorphism plus 1 1 and onto. Endomorphism means self homomorphism, and automorphism is nothing but self isomorphism. Okay, so today my topic is over. Okay students, last class we discussed about homomorphism and the types of homomorphism. Here in this class we discussed what is zero homomorphism, identity homomorphism, properties of homomorphism, and one problem based on the homomorphism. So in this lesson we discussed about zero homomorphism, identity homomorphism, properties of homomorphism, and we solve on sum. So what is zero homomorphism? So in general we know that zero function, like here also zero homomorphism. So the definition of zero homomorphism is let R comma R dash be two rings, a mapping R to R dash is defined by 0 of x equals 0 dash, where 0 dash is 0 element in R dash, then 0 is a homomorphism is called as zero homomorphism. Zero homomorphism is nothing but zero function and it is a homomorphism, that's why it is called zero homomorphism. The zero homomorphism is denoted by O, 0, big 0. So 0 of x is nothing but 0 dash. So zero homomorphism is defined as 0 of x equals 0 dash. This is very very important. 0 of x equals 0 dash, then 0 is called zero homomorphism. Then we go for identity homomorphism. So the definition of identity homomorphism is that R bearing a mapping F R to R dash, R to R, such that I of x equal x for all x belongs to R, then I is said to be automorphism, is called as identity homomorphism, So to define identity homomorphism, we take a mapping I R to R, defined as I of x equal x, then it is actual isomorphism from R to R. So that's why it is called automorphism, is called as identity homomorphism or identity automorphism. So this is identity homomorphism. Therefore, zero homomorphism and identity homomorphism are over. So zero homomorphism means 0 of x equal 0 dash. Identity homomorphism nothing but I of x equal x. Okay. Then we go for properties of homomorphism. Properties of homomorphism. So this is theorem. Let R comma R dash be two rings, 0 comma 0 dash are 0 elements in R and R dash respectively. F R2 R dash is homomorphism. Then first one, f of 0 equal to 0 dash, f of minus a equal to minus f of a for all a belongs to R, f of a minus b equal to f of a minus f of b for all a comma b belongs to R. So we have to prove these three conditions. So the hypothesis is let R comma R dash be two rings and 0 0 dash are 0 element in R and R dash, and F is a homomorphism from R to R dash. Taking all these hypotheses, we have to show that three conditions. So what the first condition? F of 0 equal 0 dash. F of 0 equal to 0 dash. So to show that f of 0 equal 0 dash, we have 0. I am applying f on both sides. F of 0 plus 0 equal f of 0. Since f is a homomorphism, f of 0 plus 0 can be written as f of 0 plus f of 0 equal to f of 0. And f of 0 can be written as f of 0 plus 0 dash, because f of 0 belongs to R dash and 0 dash is 0 element in R dash. Therefore, f of 0 plus 0 dash is nothing but f of 0. In a group, cancellation laws hold. Therefore, we can cancel f of 0 on both sides. So, we get f of 0 equal to 0 dash. So, by cancellation law, we get f of 0 equal 0 dash. So, the first property is over. So, what is the first property? F of 0 equal to 0 dash. You have to remember, because this result is used in the second part. So, what is the second part? So the second part is f of minus a equal to minus f of a. Second part is f of minus a equal to minus f of a. So to show that first one f of 0 equal to 0 dash, we started 0 plus 0 equal to 0 and applying homomorphism. Here also, to show that second part, we have to start at a plus minus a equal 0. A plus minus a equal 0. Applying f on both sides. Since f is a homomorphism, f of a plus minus a can be written as f of a plus f of minus a equal to, from the first one we know that f of 0 equal 0 dash. So in the place of f of 0 we can write 0 dash. So finally we get f of a plus f of minus a equal to 0 bar. So from this one we can say that the additive inverse of f of a is, because sum of the two elements is 0 means one is the additive inverse of the other. Therefore the additive inverse of f of a is f of minus a, but the additive inverse of f of a is denoted by minus f of a. Therefore f of minus a equal to minus f of a for all a belongs to R. So the second part is over. What is the second part? F of minus a equal to minus f of a for all a belongs to R. For all a belongs to R means if you take f of minus b, we get f of minus b equal to minus f of b. So this is true for all a, and in the place of a you can take b or c. Okay, the last one is, third part is f of a minus b equal to f of a minus f of b. So if f is homomorphism, we have f of a plus b equal to f of a plus f of b, but this is f of a minus b equal to f of a minus f of b. Okay, so if plus is there we can write. So that's why I am writing f of a minus b as f of a plus minus b, because a minus b nothing but a plus minus b. If plus is there, we know that f of a plus b equal to f of a plus f of b, since f is a homomorphism. Therefore f of a plus minus b can be written as f of a plus f of minus b. And from the second part we proved f of minus a equal to minus f of a. Therefore f of minus b can be written as minus f of b. Therefore we get f of a minus b equal to f of a minus f of b. Therefore the three parts are over. And we have to remember, If f is a homomorphism from R to R dash, f of 0 equal 0 dash means the 0 element in R mapping with the 0 element in 0 dash, because 0 and 0 dash are the 0 elements in R and R dash respectively. Therefore, the 0 element in R mapping with 0 element in R dash, that is f of 0 equal 0 dash. Second part is f of minus a equal minus f of a for all a belongs to R, and f of a minus b equal f of a minus f of b for all a comma b belongs to R. So this is the properties of homomorphism. And the problem, so we solve one problem on homomorphism. So to verify the homomorphism, some function is given. We have to verify the two conditions. What are the two conditions? F of a plus b equal f of a plus f of b, f of a b equal f of a and f of b. If these two conditions are satisfied by the given mapping, then we say that f is homomorphism from R to R dash. Suppose if any one condition is failed, then f is not a homomorphism. If both conditions are satisfied, then f is a homomorphism. If any one condition failed, then f is not a homomorphism. So the problem is, let Z be a ring of integers. We know that what are the integers, and the mapping Z to 2Z, Z to 2Z, Z means integers, 2Z means even integers. The function f from Z to 2Z is defined as f of n equal to 2n, f of n equal to 2n. So then this mapping is not a homomorphism. We have to show that this is not a homomorphism. Just I am using the different variables. Generally we take f of x plus y, x into y. Instead of x, y, take m comma n, because these are the integers. So I take m comma n belongs to z, then m plus n belongs to z, m into n belongs to z. Now we have to check that both condition. So m belongs to z, by definition f of m equal to m, f of n equal to n, f of m plus n equal 2 into m plus n, and f of mn equal to 2 into mn. Okay, we have to verify the first condition. So what is the first condition? F of a plus b equal f of a plus f of b. I take f of a plus b. By definition, because what is the definition? F of n equal to n. Therefore, f of m plus n equal to 2 into m plus n. This can be written as 2m plus 2n is equal to f of m plus f of n. Therefore, the first condition is satisfied. That is, f of m plus n equal to f of m plus f of n. So we have to verify the second condition. What is the second condition? F of mn equal to f of m into f of n. Okay, I take f of mn. By definition, f of mn equal 2 into mn. So the LHS is 2 into mn. Now I find RHS, that is f of m into f of n. What is f of n? 2m. What is f of n? 2n. That equal to, we get 4mn. But what is LHS? 2mn. But what is RHS? 4mn. So both are not equal. Therefore, f of mn is not equal to f of m into f of n. Therefore, f is not a homomorphism. So this is the function given by the problem. Given in the problem, it is not a homomorphism. Okay. So here we discussed about zero homomorphism, identity homomorphism, properties of homomorphism, and one problem we solved.